Today we will present our project, Asynchronous motor control using IR communication and a RASCO F100 inverter drive. We have implemented a system that allows for wireless, remote regulation of an industrial motor's speed and direction. Let's dive into the hardware implementation. Here you can see our physical hardware setup. The system is cleanly divided into three primary blocks. On the left is the microcontroller unit, which processes our wireless commands. In the center is the RASCO F100 inverter, acting as our frequency regulator. And on the right is the asynchronous motor, which serves as our final actuator. Let's break down the control unit first. We are using an Arduino Uno as the central control unit. Remote commands are transmitted via an IR remote controller and captured by the IR sensor, enabling fully wireless communication. To bridge this low voltage controller with a high voltage inverter, we implemented a bank of 3 relays. These relays act as a discrete, isolated switches that safely trigger the inputs on our drive based on buttons pressed on the remote. Now we will focus on the RASCO F100 inverter, which functions as our frequency regulator. The core of our control logic relies on its digital inputs, X1, X2, and X3. These terminals serve for our further control of the motor shaft's rotational speed and direction. By opening and closing our relay contacts in different pre-programmed combinations, we can change the output frequency and phase sequence of the drive, seamlessly controlling exactly how the motor operates. Here we introduce our actuator, the synchronous motor. This type of induction motor is an industry standard, widely used due to its robust construction, high reliability, and incredibly low maintenance requirements. Because an induction motor's rotational speed directly depends on its supply frequency, we can use the RASCO F100 inverter to control it precisely. Furthermore, changing the direction of the shaft's rotation is handled safely via software through our digital inputs, completely eliminating the need for wear-prone mechanical power switching. Now we move on to the actual process workflow, which we will explain in terms of an algorithm, and then later a demonstration of the entire system will be shown. Upon startup, the specified program initializes the entire sequence, keeping all relays turned off by default, so the motor is completely stopped. As soon as a user presses a button on the remote, the IR receiver handles data acquisition and evaluates the command. If button 1 is pressed, input X1 is activated, setting the motor to gear 1 in direction 1. Button 2 activates X1 and X3 together for gear 2 in direction 1. Pressing button 3 activates X2 for gear 1 in direction 2, while button 4 combines X2 and X3 to run gear 2 in direction 2. To stop this system, pressing button 0 clears all the relay signals to 0 and the motor stops rotating. Throughout this entire runtime, feedback data acquisition is done continuously. An optical encoder measures the real-time RPM and direction of the rotating shaft, sending that data straight to a custom-designed MATLAB GUI for live monitoring.